Hey there, I've got another physics GRE problem to work through with you. The one I'd like to look at is a nice easy mechanics problem about springs in harmonic motion, simple harmonic motion rather. It's number 90 on the 2001 practice physics GRE. So here it is, number 90. Follow along at home if you've got it, but I'll read it off. Number 90, 2001 exam. Two identical springs with spring constant K are connected to identical masses of mass M, as shown in the figure above. The ratio of the period for the springs connected in parallel, figure 1, to the period for the springs connected in series, figure 2, is. And then A, B, C, D, and E. A quick glance at those answers doesn't help me much. Obviously, they're unitless quantities, and it's very easy for me to mess those answers up because some of them are inverses of each other. And I'm going to be dealing with ratios here, so I want to be careful about that. But I need to solve the problem. I need to know what I'm doing to get this. I'm not going to be able to play any elimination games with the answers. So I'll be a little pedantic about this, just because I think it's a good way to, it's good to develop some of these habits. When you read that, and this may bother some of you, but it's not a bad idea to translate the words right to symbols on your paper as you would work through a problem like this. So for me this works really well. The period, which I'm going to represent by T, of situation 1, T1, the ratio of that to T2, that's how I would write that in symbols. And so I need to know what that means mathematically. And so again, this is a little pedantic, but of course that means T1 over T2. As I hinted at earlier, obviously it would be really easy to make a dumb mistake here and do T2 divided by T1, and you know they're going to put that sucker answer in there and try and get you to take that. You know that's going to be among the answers. So if this extra step helps you to get to the right answer, then it's worth the extra moment of writing this. So we want the period of situation 1 divided by the period of situation 2. And those are going to be different, of course, because of the way these springs are oriented. Now, I think this is a problem you could waste a ton of time on if you had not seen something similar to this before. As it turns out, you know what? I had not seen something similar to this before. Maybe that speaks to the poor quality of my education. But I'd not played around with springs in series and parallel before, so don't feel bad if you're in the same boat. It's really not that hard, and it's really kind of interesting. I enjoyed, looking at this a little bit. But it wasn't something I did in my freshman class or my mechanics class. So you should know how, if you play around with different springs of various spring constants, if you hook them together, what does that do? And you string them out, or if you hook them on the mass in parallel, right next to each other, how does that affect it? And so that's kind of what the heart of this problem is. And if you've seen it before, it's not a hard problem. If not, you could potentially burn a lot of time on this problem. So if you haven't seen it before, now you will have seen it before. One thing you also will need to pull out of memory here is the period of a simple harmonic oscillator. And simple harmonic oscillators are worth reviewing. Of course, you're going to run into probably several of those problems on any given physics GRE, at least one. So however you get to this equation, the period of a simple harmonic oscillator, make sure you have some way to get there. So if you don't remember this, but you remembered the angular frequency, or just the plain old frequency of a simple harmonic oscillator, that's fine. Hopefully you would be able to move from there to here. But even better is to have all three of them pretty quick and straight in your head, that you can just pop that out when you say, well, what's the period of this simple harmonic oscillator? Because of course that is what we're dealing with here. You should recognize that when you have a spring and a mass, you have a simple harmonic oscillator. It's a linearly restorative force, like Hooke's law is. So there you go. Basically what we're going to need to do is get situations for the two diagrams, 1 and 2, and divide those by each other. So I'm kind of talking too much here, but the situation 1, what is the period of this? is going to be 2 pi, and in our case m is big M divided by k, and what I'm going to call this is KEQ1, and that is going to be the equivalent spring constant. And so because I have two springs, I want to work out the equivalent spring constant. And how do I do that for situation 1? I'm going to derive this at the end of the video, so I'm going to go through this fast now. If you want to hang around and watch the rest, great. Otherwise, you can move on to another video. But the equivalent spring constant in situation 1, so KEQ1 is just equal to K plus K, equal to 2K. When you add springs in parallel like that, you just add the spring constants to get an equivalent spring constant. So that's just 2K. So I've got T1 worked out there. I'm going to give myself a little more space because this one's a little different. But T2, of course, that's just going to equal 2 pi times big M over KEQ2. What is KEQ2? What is the equivalent resistance in the second situation, where you can see those two springs are connected to each other? They're kind of lined up there. As it turns out, the very short version of this that I'll go into the derivation afterwards is that these springs in series add very equivalently. You probably remember from circuits how resistors add in parallel. In other words, you get 1 over KEQ equals 1 over K1 plus 1 over K2 plus ... 1 over K sub n. So that's how you would add those to compute an equivalent spring constant when they're in series like that. In our case, we only have 2 of them, so it's not hard, but we get 1 over KEQ2 equals 1 over K plus 1 over K, and that equals 2K over K squared. Just do the algebra there, you'll get there. And that equals 2 over K. And then you have to invert it, of course. So to get KEQ2, you get K over 2. And that may surprise you. I mean that you're using 2 springs, but you're getting, in a way, you're getting half as much of a restorative force there, or in other words, your spring constant is half as much. It seems a little weird until you actually work through in your head what's going on, and I encourage you to do that. But that's what it is. That's the equivalent spring constant in this situation. So all you have to do is go back and plug all of this junk in, and be careful to, you know, cancel the stuff out correctly. So you get 2 pi over root big M over 2K divided by 2 pi over root big M divided by K over 2. Running out of space there. Hopefully you're solving that on your own sheet of paper at home, because it's bound to be neater than my workout here. Anyways, you're going to cancel that junk, and just, you know, to divide by that stuff, just invert, multiply. Again, taking an extra step there, if it keeps you from making a dumb mistake, is certainly worth it, right? So K over 2 over M. That's kind of how I would work my algebra there. And so you see the M's cancel and the K's cancel, and I get square root of 1 over 4, and that equals 1 over 2, 1/2. And so I'm going to scan my answers at that point, and of course I have that, as well as lots of answers where I could make easy mistakes and end up with the wrong answer. But answer A is 1/2. That's the correct answer that I would want to pick. So okay, that's the shorter version explanation of how to do that problem. So by all means, if you're content, move on, look at another problem or whatever. If you want to see the derivation, how the springs work that way, then stick around here. I'll take a couple minutes and try it. I think the more interesting of the situations is when you connect these springs in series. So if you do something like this. Okay, so if I'm pulling out here or attaching a weight or whatever it is I happen to be doing to extend this spring by some distance, which I'm calling x sub t, the total distance, I'm going to stretch all of the springs, and they're going to potentially move different distances. So I'm calling this spring 1, spring 2, spring 3. And I tried to draw them so they looked a little different, kind of like a big spring, a little spring, and a medium spring there. They will, in fact, stretch different lengths because they're of different strengths. And so I've also shown that they have different spring constants there. And this is a specific case. The general case would be, you know, n number of springs. I could add many more, not just 3, obviously. And so I want to show how you get, I'll have to clear my board here and start over, but I'd like to show how you get to that and show how you can hopefully help you see why when you put springs like that in a series, why they add similar to resistors add in parallel, why they add like they do, basically. And so the equations that I would use, and this is, well, this one is really interesting. One thing to realize here, if you isolated one of these springs, so if I redraw this spring down here that's supposed to be the big spring, we're going to assume all these springs are massless, of course, as you usually would in these problems. If I isolated the free body diagram of the spring, it's not a dynamic system, so the spring is not moving. So we know the forces in any given axes are balanced. And the forces that we're going to have, we know that this force is pulling out that way. The whole system is not moving either. And so I'm sorry if I'm not being as thorough as I could be, but to me that just screams that this force here has to equal F, whatever force on the end is. Because, you know, if I drew the free body diagram of all 3 of the springs and looked at the external forces acting on those springs, well, they're not moving either. So their forces are equal and opposite. And if I have a force acting here to the right, then I have one acting to the left. It's got to be there on this wall that I've drawn in. So that's got to be force F. If this individual spring is not moving either, and it's not, then this has to be F too. And this is kind of interesting to me. It kind of rings of like the tension in a rope. When you look at any given piece of a rope, you know, you can say that the tension is equal anywhere in the point on the rope, any point on the rope. As it turns out, for any one of these given springs I can draw, the forces on the ends of that spring are equal. F, you know, whatever this would be, whatever force is working to displace the entire system goes all throughout all of the springs. And maybe that's completely obvious to some of you, but if it's not, then I'm being very pedantic about that. But anyway, so the other thing to note here is what is F going to be in the case of this specific spring? And that's where you go to Hooke's law, because you know that that force it's an equal and opposite reaction pair. So in order for this force to be here, this spring must also be pulling back with forces F here and here, right? And what's interesting is those forces are gonna, you know, work by Hooke's law. So if I displace, and I'm being sloppy here, I apologize with my signs and you know, my vectors, which way is going which, but this is going to be equal to kx because it's going in that direction. So if I displace the spring that way, then the restorative force is going to be back this way. Magnitude, and I'm sorry, this would be k1 times x1. And so that is however much this big spring is displaced multiplied by the spring constant of that spring. And so this provides you with a really interesting equation that relates all of the spring displacements as well as the spring constants. What this is saying is that F, the restorative force, is equal to K1 x1 is equal to K2 x2 dot 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 is equal to Kn x sub n. So even if I had a whole bunch of those springs together, that's how they would be related. That force kind of ties their displacements and their spring constants all together in this manner. These are all equal. Okay. The other relation that I would do a derivation out of this, where I would start my derivation, is that, of course, my total displacement, I add all of the other displacements. So in the general case, for n amount of springs connected together in series is just the displacement of the first spring plus the displacement of the second spring plus dot 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 the displacement of the nth spring, and that equals my total displacement. Okay, now if I make some substitutions here, now this other relation that I've worked out here is the restorative force equals my equivalent, okay, my equivalent spring constant multiplied by the total displacement, and that is equal to any one spring, the spring constant of that, times the displacement of any one spring. Okay. Kn x sub n. Okay. Then I can start making a substitution here. I can divide this equality by KEQ, and I get all of these relations, and I get x sub t. Oh, I'm sorry, I don't think I want to do that. What I want to do is get x sub 1. And so I would want to solve for x sub 1 to substitute up here. So I guess I'll need to leave both of these. But if I was to solve for x sub 1 using this in terms of KEQ and x sub t, then I would get x sub 1 equals KEQ x sub t divided by k sub 1. Okay. So I'm sorry, I'm going to write that and then I'm going to erase this second part, and I'm going to start making those substitutions up top. Hopefully that'll make sense to you. So for each of these displacements terms, that is going to equal KEQ x sub t divided by k sub 1. This would be KEQ x sub t divided by k sub 2 plus dot 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 KEQ x sub t divided by k sub n. And so hopefully you're starting to see this pop out here. That is equal to x sub t. Now I've got x sub t in each of these terms, so that's going to cancel out. I can divide both sides of this equation by x sub t, and then I'm just going to get 1 equals KEQ divided by k sub 1 plus KEQ divided by k sub 2, etc. Okay? I know I'm going to run way long on this video, hopefully not too long. But there you go. And then you can divide by KEQ, and you get 1 over KEQ equals 1 over K1 plus 1 over K2 plus dot 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 1 over K sub n. So if you hadn't seen that before, that's kind of how you get there. Springs are nothing like resistors or capacitors, obviously. They were completely different, but they just so happen, you can see in this derivation, to come out the same way. It's kind of an inverse law here that you have to calculate that equivalent spring constant with. So there it is. That's in series. In parallel, it's actually pretty easy. I'll try it. I'll try it real quick. The trick about parallel that's kind of stupid is it's really an idealized situation, because obviously if I had a mass here, and in a real situation, any real life situation where these springs were different, you'd get torques going there as you pulled this, because they would exert different forces, and you get torques that would try and rotate this. So in an idealized situation, you're imagining these are attached at exactly the same place, and there's no torques or whatever. So that's kind of a weird way to look at it. But anyways, so here's your mass M, I guess. We'll look at this situation, and you have N springs that are attached. Now what's to note here is that they all get displaced. You know, this is x1, x2, x3, dot dot dot, x sub n, however many springs you have there. Obviously those are all going to be the same. They're going to be equal to the total displacement, and that's all going to be the same. So the forces, the restorative force by all those is going to equal negative kx. And then the total force, this is for any one of those, and so the force total is going to equal, you know, negative k1 x1 plus negative k2 x2 dot 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 k n x sub n. Now when all of the x's are and this and f sub t, okay, so I'm gonna show you what I got there. F sub t equals negative k eq times the total displacement there. But in our situation, you should realize pretty quick that x sub t equals x sub 1 equals x sub 2 equals x sub n. The total displacement is the same as the displacement of all of the springs, because they're in parallel. Hopefully you can see that. And so that's going to be on both sides of the equation, and you can just divide it through. And the negative sign is going to be on both sides of the equation there, so you just get k eq equals k1 plus k2 plus dot 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 plus k sub n. You just add the springs there, and intuitively that one seems to make a lot more sense than the other one when you do them in series, which seems kind of backwards. You're adding springs, but the restorative force gets less. Okay, so you know, bless you if you hung on through all that, and hopefully that derivation helped you. I know this video's gone really long, so I'm going to wrap it up and see if I can upload it, and I'll see you next time. Thanks.